Most people interact with large language models through trial and error. You type a request, read the output, and tweak a few words until the response looks right. It works for simple tasks, but it relies on guesswork rather than a reliable structure. When you attempt to apply this method to enterprise-level software, the fragility of the approach becomes obvious. Unstructured natural language instructions often collapse under their own weight. An instruction that works on Monday might fail on Tuesday after a minor model update, leaving you with disorganized outputs. Because there is no standardized way to describe these trial and error tweaks, developers can't easily collaborate. Without a shared professional vocabulary, a specific technique used to fix a prompt remains an isolated hack rather than a reusable engineering solution. The solution requires a shift in how we formulate inputs.
Instead of treating prompts as domain-specific text hacks, we can treat them as structural invariants, rules that define how the prompt operates regardless of the specific topic. In 2023, researchers White and colleagues published a framework to solve this exact problem. They proposed categorizing specific prompt behaviors into a formal catalog. They drew a direct parallel to the classic Gang of Four software design patterns. Just as object-oriented programming uses established patterns to solve recurring problems, prompt engineering can use established language structures to define specific AI behaviors. This illustrates the transition from a messy pile of random text instructions to a structured methodology that resembles a precise software blueprint. Within this framework, the researchers isolated 16 distinct design patterns, organizing them into 6 formal categories. These categories govern every phase of interaction. They control input semantics, customize how outputs are formatted, identify errors in logic, improve the user's initial prompt, define the interaction flow, and manage what the model is allowed to remember. Standardizing these interactions provides the foundation for building reliable systems on top of unpredictable language models. To implement these patterns, we have to examine the mathematical logic governing them. We can represent the smallest unit of prompt logic with the single variable shown here, SI. This variable represents a fundamental contextual statement. It is an absolute directive, a structural rule the model must follow to enact a specific pattern. By injecting this statement into the context window, you close off certain probabilistic pathways, restricting the model to a specific set of behavioral parameters. A single directive is rarely enough to build a robust application. Conjoining these statements creates a complete operational rule. This creates the foundational equation of the framework. A prompt pattern is the logical conjunction of these fundamental statements. This framework treats the prompt as a conjunction of logical rules, rather than a conversational request. We can see this logic in action within the prompt improvement category. Left to their own devices, large language models often struggle to resolve complex, multi-layered reasoning tasks. If you submit a multivariable question in a single shot, the model attempts to generate a complete answer in one pass. This often leads to immediate hallucinations or gaps in reasoning. To solve this, the catalog defines the cognitive verifier pattern, applying a structural mechanism to force the model to decompose the problem first. In this diagram, the first invariant step explicitly instructs the AI to break the user's initial question, Q, into a series of smaller, manageable sub-questions. Next, the model is required to answer each of those sub-questions sequentially, generating a distinct answer block for every node. Generating these intermediate steps helps prevent the model from attempting an unsupported leap in logic. Finally, the pattern dictates that the AI must synthesize those individual answers into a final output calculation. Because this synthesis relies on the logic established in the preceding subanswers, the accuracy of the output improves compared to a standard naive guess. The cognitive verifier pattern forces an algorithmic chain of thought, transforming text generation into a step-by-step reasoning process. We can exert similar control over the flow of the conversation itself, using the interaction category of patterns. This flowchart outlines the standard sequence of initiative. The user asks a question, and the model provides an answer. The difficulty with this dynamic is that users often lack the technical parameters the model needs to execute a complex task properly. To correct this, the framework introduces the flipped interaction pattern. You apply a fundamental contextual statement that inverts the direction of the interaction. Now, the model asks the questions, and the user provides the answers. The language model is structurally bound to interrogate the user, asking targeted questions one at a time to gather context. The paper highlights a practical example, using this pattern to generate an AWS CloudFormation deployment template. Rather than the user attempting to list every specification up front, the LLM pings the user for architectural requirements, like database sizing or network routing, that a human might otherwise forget to include. This cycle continues until a specific evaluation condition is met. Once the model has sufficient data, the loop halts and the final AWS code is generated. Flipped interaction increases the likelihood that critical variables are collected while reducing the cognitive load on the human operator. The power of this framework is most visible through pattern composition. Because each pattern acts as a discrete logical rule, multiple patterns can be stacked within a single prompt to govern different aspects of the interaction. Consider an application that requires the model to adopt a specific identity, dictate the flow of the conversation, and format its output rigorously. You achieve this by compounding the fundamental contextual statements into a single composite equation. This combination is used in the paper to build a technical interview simulator. The persona pattern establishes the constraints of a senior engineer. The flipped interaction pattern drives the sequential questioning. Finally, the template pattern forces the model to output its feedback as a formatted JSON object. This creates a specific multi-turn interaction without writing traditional code. Pattern composition allows you to architect complex logic gates through natural language, creating interactions that function like standalone software. However, heavily conjoined composite patterns introduce engineering trade-offs. This gauge illustrates the first major constraint, the context window. Elaborate structural rules consume a significant volume of tokens just to establish baseline parameters. This token usage limits the model's remaining memory capacity for the actual user input and the ongoing conversation. The second major risk is instruction following decay, particularly when running complex constraints through weaker models. As the conversation deepens, an overburdened model may drop earlier constraints, breaking the agreed-upon structure and reverting to conversational filler. Engineers must balance the structural complexity of their composite patterns against the specific computational limits of the model being used. The prompt pattern catalog provides a structured methodology to navigate the latent space of large language models, moving prompt engineering from ad hoc guesswork toward a systematic design discipline.